The next topic is how to do some Bode plot approximations based on a transfer function that is a little bit more complicated. So for now, we're going to be looking at a pole. It's still a zero. Still a very simple Bode plot. What happens when we have s plus some constant a? This is a common zero that we're going to see in our function. So what does that look like on its own on a Bode plot? And we're using the generic a. I'm not saying a specific value. So this, luckily, will have a general way to plot the Bode plot with any value of a here. So let's take a look at this. And instead of going through and making that table every single time, which can be a little bit tedious, we're going to look at some quick ways to approximate this Bode plot of this function. So we're going to take two steps first. First, we're going to look at when s, so s equals j omega, is, well, I guess we're going to say much less than a. Okay, so when we're very low frequencies, they don't really affect this a. So this is a very small value, or a will dominate. So g of s here, I guess we'll say j omega, right? Because that's what we're looking at. It's approximately just a. So at very low frequencies, we are going to assume that our frequency response, or our transfer function, just looks like a. First, we're going to actually change these scales. So instead of being an absolute, now we're going to do multiples of a. So a times 10, a times 100, a. So these are different multiples of whatever the value of a is, and same here. Okay, so we're just scaling our x-axis a little bit differently based on the value of a. Okay, so at very low values, our transfer function will essentially be a, which means that from here, our magnitude is essentially going to be, and I'm going to do it in dB, so it'll be 20 log a, whatever the value of a is, and that'll be in dB. Okay, so let's say we have, so again, we don't know exactly what this is going to be. We're going to call this 20 log a here. So the scales here are going to be this value, 20 log a plus minus 20 plus 20. Anyway, this scale. So we're just scaling our x and y here to fit with our ambiguous value of a here. Okay, so at the beginning, at low values of j omega, small values of that, of j omega, then we're going to essentially have our magnitude be equal to 20 log a. Okay, so that's kind of coming up over here. So we know that in the low side over here, we're going to start at this point. And our angle of this is 0, right? So our angle is going to be of a just equal to 0 degrees. Okay, so we know we're going to start at 0 here at the beginning. So let's now jump over to the other side when we know that this is one case. Now let's say s equals j omega is much larger than a, right? So in this equation, if this is really large, this kind of doesn't matter anymore. So our g of j omega will be approximately just j omega, right? So just the s here. So if we look at that, we can see that, well, we already did this, right? So we looked at just the case of when g is equal to s. That's the same thing as here. So we know that, I'm going to do the angle first. Theta g is equal to positive 90, right? So we know that that's going to, as we go to infinity, we're going to go towards that angle, that phase, and the magnitude is going to be increasing. Before, remember, it was increasing at 20 dB per decade. So we'll know that the magnitude will be increasing at 20 dB per decade, which is what you would get if you take that and you plug it back into our magnitude equation. You can do all the math again for that. So we know that we're going to go towards 90, positive 90 degrees here as we go to infinity. And we're going to be increasing at some rate. Now the next part is where the approximation comes in. What we can essentially do is, we know that A is our turning point here. So we can approximate our turning point as essentially our line goes approximately to there, and then we'll start to go up at 20 dB per decade. So I'm just drawing some lines here to approximate. So we know what we look like on the left, we know what we look like on the right, we just kind of bring them together, and this is our approximation for how the magnitude will change over this area. Same here, we know we're starting at 0, and we need to get to 90, and this is kind of our middle point at A, so we end up approximating this as a linear line. We start approximately here. And it's just a linear line between these two. And we draw the lines from, I believe, 1 decade below and 1 decade above. So this will be approximately increasing at 45 degrees per decade. So to go from 0 to 90, we go 1 decade below and 1 decade above, and that would be our approximate line from our 0 to 90. And then here we know that we're increasing at 20 dB per decade because we have the 1s here that dominates as we go to increasing frequency, as we go to infinity. So this is not exactly correct. So if we go through and actually plot this point, and you can see in the book they have, or if you plot it on MATLAB, you can see this difference. It's not exactly, it'll change differently here, but this is a good approximation for drawing a Bode plot. So you can see how it changes, and this is an approximation for the change in the phase. Okay, so we do this, so to reiterate what we've done, we're looking at a single 0 and how it affects the Bode plot. So we look at what it looks like before it hits A as very small values of frequency of omega, and then as it goes to infinity, how it changes. So S will dominate at very large values. So the Bode plot will essentially shift from just an A by itself to an S by itself. And so we just approximate that transition here with straight lines coming into the point right at A, and here it goes through 45 at the point A. Okay, so this is how you approximate a 0 using a Bode plot.